mu du equals 0 for all t greater than 0. Then we call this as a null function. Okay. So actually we saw that 0 to infinity but actually the function I gave actually this is the correct function. The function that I gave last time was not the real null function. Okay, so this is correct. Okay, now let me do this one. Okay. Let me say that this is a null function. Okay, so the function is defined as ft equal to it has been defined as it has been defined as 1 minus 1 0 otherwise. No? So it is 1 then t equal half. This change is 1. So this is minus 1 then t equal 1 0 otherwise. Okay. So null function in what? What is the definition of null function? 0 to t, capital Fu, du 0. Okay. If 0, then we say Fu is a null function. Null function. Okay. So this is the definition of null function. So now, if we find the integration 0 to t Fu is equal to, you see, when t equal half, function is what? When t equal 1, function is minus 1, otherwise 0. So if you draw this function actually, draw this function, it will be like this. When t equals 0, okay, so the function is 0. So up to this point, the function is 0, but when t equal half, function is actually 1. This is half. Then again the function is 0. When t equal 1, the function is minus 1. So this is minus 1. This plus 1. Actually, the function is actually point. So if you calculate the area of this one, what is the area? All the areas are 0. That's we have just 2 points. So this is called null function. Okay. So this is called null function. If you have points, then so if you calculate this one, this is equal to what? 0 to half plus. No? You can say 0 to half. 0 to half. So you can say 0 to half minus. Just before that. Just before that. Half minus. So the function is 0. Plus and half minus 2. Sorry. Half minus to half plus. That means simply when function is 1. So when function is half, so function is 1 actually. Plus half plus 2, 1 minus. Again the function is 0. du plus 1 minus 2, 1 plus. The function is minus 1. Du plus 1 plus to t. Function is 0. Okay. So if you calculate this inequality, if you calculate this integration, okay, so everything is 0. You can see that this is 0, this is 0, this is also 0. So this becomes actually minus half to half mean point. So that is that we have half to half 1 into d plus 1 to 1 minus 1 into d. So this is also 0 plus this one is also 0. Therefore function is 0. Right? So in the similar way, if you use the definition of, so if you have a null function, then the Laplace transform of null function is always 0. Okay, so you can verify that. You can verify 0 to infinity e to the power minus st into e to the power minus st into a. So if you verify this one, okay, into verify, you can see that this is equal to 0. Because for all values it is 0. For all values it is 0. Therefore, this is 0. Okay, this is 0. Therefore, you can say that this is a null function. So, if you have a function ft, so Laplace transform of ft plus null function, then this is equal to f, isn't it? Therefore, if you add the null function with any function, okay, this is same as Laplace transform of f. Therefore, if you add a null function with a function, if you add a null function with a function, then the Laplace transform is not unique. But if you don't have a null function, if you don't add a null function to a function, so if you don't, so if you add the, say for an example, this is null function 1. Say for an example, this is null function 1. So null function 1 also the function is fs. If another one say ft plus another null function in 2t, then this is also same as fs. Why? Because using the linearity property, you can say that Laplace of ft plus Laplace of n2t. But this is 0 now. Therefore, this is same as Laplace of ft. Therefore, if you had a null function, then you will get a, therefore we can say that, therefore inverse Laplace of fs is not unique. Because you see, inverse when you take fs, sometimes you can add n1, sometimes you can add n2. Therefore, it is not unique. Okay? But if no null function is added, if no null function is added, then inverse Laplace is unique. you have to understand this. If no null function is added, then we can say that Laplace is unique. Otherwise, it is not unique, right? So please change this one, because the last class I made a mistake. In the sense that I actually got a different idea and explain this one, but this is the correct one. Okay, this is the correct one. This function is correct. Okay. Now we are discussing inverse Laplace, but anyway, it is not that much important. If you don't even understand, don't worry about this. So what here under this one we are trying to say is the inverse Laplace transform function is not unique. Okay, but if you don't add a null function, then that is unique. So that is what finally we are saying. The inverse Laplace transform is unique except for the addition of null function. Okay. Right. So then we in the last class we studied about the linearity property of this one. Also we studied the first shifting property. Okay. So these two things we studied in the last class. Now we are going to talk about the second shifting property. The second shifting property. Okay. The second shifting property is actually, let me explain that second shifting property. Okay. Now the third one, we are going to talk about the second shifting property. Second shifting property. Okay. So we know that the Laplace transform of say Laplace transform of say ft equal to fs. Okay. So Laplace transform ft equal to then Laplace transform of f of t minus a into h of t minus a. Can one of you tell me the answer for this? Where h of t minus a is the Heaviside unit step function. And one of you tell me the answer for this. What is the second shifting property? Actually, this is the second shifting property of Laplace transform. So can anyone text me the answer for this? What is the Laplace transform of f of t minus a into h of t minus a? Yes, good. So we have that e to the power minus a into fs. Therefore, the inverse Laplace transform of e to the power minus a into fs is equal to, you can say that f of t minus a into h of t. Okay. So this is the definition. So if you want, you can write this as this is equal to, if you want, you can write this as this two. Let's just simply say f of t minus a is a 0, because we know that when t is greater than a, this is 1. Okay. Because the reason is why, you can write this way also. Okay, because we know that so both are equal. Okay, both are same. You can either give the answer in this way or you can give in this form. You can give the answer in this form. Okay, because we know that h of t minus a equal 1 if t is greater than is equal to 0 if t is less than. Therefore, in this interval, I am putting h of t minus a equal to 1. Then you will get f of t minus a. Otherwise, this is equals. So, if you have a function multiplied with e to the power minus as, then always you can write it in this form. This is the inverse Laplace transform this form. Okay, so you have to do a lot of practice, then only you can become familiar with these kind of things. It's like integration. Normally, inverse Laplace transform is normally we know that differentiation is easy compared to the integration, because integration is actually the converse of the differentiation, isn't it? So we are doing the reverse of the differentiation. Therefore, that is somewhat, somewhat difficult compared to the differentiation. Similarly, the inverse Laplace transform is somewhat difficult compared to the Laplace transform. Okay, because we have to do some guess. Okay, so we have to do some lot of guesses to find the correct transformation. Therefore, you have to do a lot of works. Then only these things will become familiar to you, right? So let's have an example to understand this a little further. So proof is given here. Proof is not necessary because this is actually we are using the inverse Laplace transform proof, Laplace transform theorem to prove this one. So this proof is not much big deal. Okay. So let's try to find out the value of this one. Okay. So s plus 1. So here the question is, we want to find the inverse Laplace transform of s plus 1 e to the power minus phi s divided by s squared plus s plus 1. Okay. So actually, so you can apply more than one, you may have to apply or you may have to use more than one theorem to find the answer of a particular inverse Laplace transform. Okay, so I'm going to do this question part by part. Look at here. So you have to develop, you have to do a lot of practice, and you have to develop some more ideas. Okay, so that is the purpose of that part. Right. Okay. Now I know that. Look at here. First, I'm going to find the inverse Laplace transform of s plus 1. So, okay, s squared plus s plus 1. I'm going to find the inverse Laplace transform of this one first. Okay, then here it is, you see, it's like e to the power minus as is multiplied with this fs. So if I know the inverse Laplace transform of fs, then simply when it is multiplied with e to the power minus as, then I can use the Heaviside step function and I can easily write it. Therefore, finding the inverse Laplace transform of fx is the problem here. Therefore, if you can find the inverse Laplace transform of this one easily, then you can write the inverse Laplace transform of this into e to the power minus phi fs is very simple, isn't it? Therefore, I'm going to find the inverse Laplace transform of this one. Okay, there are many ways of finding inverse Laplace transform. One is you can use partial fraction. First thing, you can use partial fraction, but you cannot factorize this one, isn't it? It is very difficult to factorize this one. Okay, this is difficult to factorize this one. So what we can do then? Any idea for this one? Okay, so let me see that how I am writing this one. So you have to actually, we cannot teach everything. You have to do a lot of practice, then automatically it will come to you. I'm writing this way. Look at here, s plus half, s plus half divided by, okay, s squared plus s plus 1, I'm writing it as s plus half whole been squared plus, so when I expand this one, I will get s squared plus s plus 1 over 4. So I can write this as, the remaining is 3 by 4. So I'm writing this as square root of 3 over 4 whole been squared. I can write this way. Okay. So here I'm going to split this into two. One is inverse Laplace transform of s plus half over s plus half whole square plus, sorry, here I have made a mistake. It should be 2, no? It should be 2. Plus inverse Laplace transform of half into okay. So this is how I can write it. If you see in the numerator part also I have made s plus half, the denominator part also I have made s plus half, because here I am going to use, otherwise if you write it other be able to use the first shifting property. Okay, so I am going to use the first shifting property here. So first shifting property says is what? Can anyone tell me the first shifting property? First shifting property says that, look at here, L of ft, okay, if L of ft equal to fs, okay, then Laplace transform of e to the power at into f of t equal to f of s minus a, isn't it? So here, look at here. I have something like, if you think that s minus a as s plus s minus half, then you can simply think this as your ft, isn't it? So using that one, what you can write is, you can write this as, okay, so this is actually, if you look at, if you just consider, if you just think this is your s and this is your s, because we have the same, and this is your s. So what we have, s over s squared plus 3 by 2, isn't it? So s over s squared plus 3 by 2. So this is actually in the form of cos square root of 3 by 2 t, isn't it? So but actually we have half also. So you can write this as, actually this is equal to actually this one. Okay, this one is equal to, you can write it as e to the power minus half t, because for a you have minus half, because here you can minus half. You can write this as s minus minus half. So you can write it as e to the power minus, because when you have something like this, then you have L inverse f of s minus a. You can write it as e to the power at into f of t, isn't it? F of t. So you can write this way. That is why here, instead of a, I have minus half. So my a value is minus half t into, this is actually nothing but cos root 3 by 2 t. Cos root 3 by 2 t. Here, plus, similarly, if you look at here, this is nothing but actually this similar to this one. You can think like here, actually when you do the Laplace transform of sin at, we have actually a over something, no, but we don't have a here, so we have to make that a here. So how you can make that a here? So you can bring this half here and you can multiply by 3 by 2 and 3 by 2 here. So that will become, so let me take the half out. So I'm writing this part, okay. So half out, and then if you multiply by 3 by 2 up and here 2 by root 3. Then this is actually Laplace transform of, okay, root by 3 over s plus half all in square plus root 3 by 2 square, isn't it? Therefore, this is nothing but sine root 3 by 2t. Okay, but here actually instead of s, what we have s minus half. Therefore, you can write this as plus e to the power minus half t, e to the power minus half t into sine root 3 by 2t. But don't forget, when you simplify this one, there is a 1 over 2t. There's a 1 over 3. Okay. There's a 1 over 3. Therefore, if we simplify this one, we can write it as e to the power minus half into, we have cos root 3 by 2 t plus, sorry, plus 1 over root 3 sine 3 by 2. Okay, so actually this is our ft. This is actually Laplace transform of this function. Now what we have original is multiplied with what? Minus pi. So you see here, when a function is multiplied by e to the power minus as, that is nothing but f of t minus a into h of t minus a. Okay, f of t minus. So when it is multiplied by e to the power minus as, you have to multiply by h of t minus a, as well as you have to change all your t as t minus a. So the value of a here is, minus pi. So this is your value a here. Therefore, you can say that Laplace transform of s plus 1 over s square plus s plus 1, okay, into e to the power minus pi s is nothing but f of t. So f of t means inverse Laplace transform, this one, that we have got this here. So that is what, so wherever you have t, you have to change it by minus pi, t minus pi. Therefore, e to the power minus half, okay, t minus pi into first square root of 2 t minus pi, because you have to change all t as t minus pi, plus 1 over root 3 into sine root 3 over t into pi. Not only that, you have to multiply this with what? H of t minus a. So h of t minus a, actually you have to multiply with h of t minus a. Your a is actually pi. So that is the answer. So here you can see that whether the answer is correct. Yeah, the answer is correct. Do you understand this? Do you understand? Yes or no? Please tell me, do you understand this? Can one of you answer me, please? Use the chat box to answer me, please. Okay. So here actually we are using the second shifting property here. Okay. So here, so using, if you want, you can write it using second shifting property. Okay. Here actually we are here using the first shifting property. Here we are using the first shifting property. Okay. So anyway, answer is given here. Please try to understand this here. Okay. So you have to do a lot of practices here. So we'll move to the fourth one, that is called the change of scale property. Change of scale property. So let's see what is change of scale property. Change of scale property. Change of scale property. So we know that Laplace transform of f of a. Can anyone tell me Laplace transform of f of a? What is the Laplace transform of f of a in terms of Laplace transform of f of t? Can anyone tell me that? Use the chat box. Only the 77 is responding. What about others? Otherwise, I will have to call names. Yes. So Laplace transform of f of a t equal to so we know that 1 over a into f of s over a. Now, so if instead of a, if I put f of 1 over a t, then what is the Laplace transform of this? Instead of a, I am putting 1 over a. So wherever I have a, I am going to put 1 over a equal to f of s over, isn't it? So this is equal to a into f of, so this is 1 over a, so it goes up and we get a's. Therefore, Laplace transform of, because a is a constant, therefore you can say that Laplace transform, inverse Laplace transform of f of equal to, so you can take this a this side, 1 over a into f of, so this is the proof of that one. So if you have something a into s, then you can simply use this line. So this is called, the change of scale property of inverse Laplace transform. This is called the change of scale property of inverse Laplace transform. Okay, let's have an example. Yeah, so we are given that inverse Laplace transform of s over s squared plus 1 all whole squared. We are given that inverse Laplace transform of s over s squared plus 1 whole squared equal to, it's given, okay, it is given. This example. So we are given that is equal to half into t sine, half into sine. So half into t into sine. Okay. Then we are asked to find the inverse Laplace transform of 32s, okay, 16 s squared plus 1 So this is what we want. Okay. So you see, when you have S, you know the answer. When it is multiplied by AS, then that is 1 over A into F of T. So we'll convert it that. So you can write this as. Okay, so see, I can write this as inverse Laplace transform of 4S over, because why I am writing 4S? Because here I have 16x only. Therefore, I can have 4 only here. Therefore, I am taking my 8 here. 4S whole square plus 1 so I know the Laplace transform is so S square plus 1 whole square. So now the value of my, so I know the value of this one. So this is my Fs. Then if I take this as my Fs, okay, so if I take this my Fs, okay, if I take this as my Fs, okay, if I take this as my Fs, then this is nothing but F of 4S, isn't it? Wherever you have S, if you put it 4S, then you will get this one. Therefore, this is equal to 18. F of A is, what is the inverse Laplace transform of F of A is? 1 over A into F of T over. So 8 into, so 1 over A, my A is 4. So 1 over A means 1 over 4 into T over A, F of T over. Wherever you have T, you have to replace it by T over 4. But here, this is your F. Isn't it? This is your F. Wherever you have Ft, you have to replace it by T over 4. Therefore, again you have half into T over 4 into sine T over 4. That is, we are replacing all T by T over 8. So if you simplify this 2 over 8, this 8 can cancel, then we get T over 4 sine. Okay, so that is the answer. Do you understand? Zero zero 5, do you understand? 005, are you there? 006, are you there? 009, are you there? 10?
Yes, sir.
14, are you there? Hello, 14, are you there? Twenty-one, are you there? Twenty-one.
Yes, sir.
Right, okay. 47, are you there? 68, are you there? 81, are you there? 81. Hello, 81, are you there? 106, are you there? 106. Okay. Anyway, so that is change of scale property. Now we'll move to the fifth one, which is called the inverse Laplace transform of derivative. inverse Laplace transform derivative. Okay. So here this is very important one. Look at this. All are important, but this is somewhat tricky, so you have to understand this carefully. Now, to the fifth one, inverse Laplace transform of derivatives. Inverse okay. So carefully understand this one. Right. Now we know that if Laplace transform of ft equal to fs, then Laplace transform of dn f of t, sorry, sorry, not this one, t to the power n into f of t, where n is a positive integer, where n belongs to set of natural numbers, is equal to what? Can anyone tell me the answer? Laplace transform of ft equal to fs. Then what is the Laplace transform of t to the power n into ft? We have studied as one of the theorem. Can anyone answer me this question? What is the Laplace transform of t to the power n into f of t? I'm waiting for your responses. Yes, good. So that is minus 1 to the power n into fn s. That means that the nth derivative of this one into minus 1 to the power n. Therefore, we can say that the inverse Laplace transform of the derivative of this function equal to, okay, so I can bring this minus 1 to the power to this side. Therefore, I can say minus 1 to the power n into t to the power n into f. So, if you know the Laplace transform of a function ft, if the Laplace transform of a function is fs, then its nth derivative, inverse Laplace transform of its nth derivative will be minus 1 to the power n into t to the power n into f of t. So, this is the theorem. This is the theorem for the derivative of inverse Laplace transform derivative. Say for an example, okay, right. So we'll have an example. So let's discuss this example. So we want to find Laplace inverse Laplace transform of S over S square plus 1 or root square. So you want to find the Laplace transform this one. So this is actually, we don't have any direct form of this one. We didn't have any direct, we haven't studied, we haven't seen any direct Laplace transform of this kind. Okay, because here we have squared here. Here we have squared. Okay, here we have squared. Therefore, we have to think of alternative. We have to think of alternative. Right. Okay. Now let me say, what is the inverse Laplace transform of 1 over s squared plus 1? What is the inverse Laplace transform of s squared plus 1 over s squared plus 1? What is the inverse Laplace transform of this one? Can anyone tell me the answer? But this is direct one. This is direct one. Can anyone tell me the answer? Yeah, that is sine. Good. This is equal to sine because we have that sine at equal to the Laplace transform of sine at equal to, we know that a over s square plus a square. So a is equal to 1, isn't it? So that is sine a. Now, what is the derivative of this function? So if you say this is your fs. Say if you take your fs as 1 over s square plus 1. Now, what is the first derivative of this one? What is the first derivative? F dash. What is the first derivative of this function? So if we differentiate this one, this is nothing but minus 2s over s square plus 1 all square. Isn't it? Therefore, actually, here, what we want to find is actually the derivative of this function. Isn't it? Derivative of this function. But we have, in addition, we have minus 2. We have minus 2. Therefore, from this one, we can say that the Laplace transform of minus 2s over s squared plus 1 all in square equal to what? Equal to what? Minus 1 to the power n. Actually, it's the first derivative, isn't it? So minus 1 to the power n into t to the power n. So t to the power 1, because the value of n is equal to 1, t to the power n into, isn't it? The first t to the power n into ft. So ft is what? Actually, this is our ft. That is equal to sine, isn't it? So that is equal to sine. But actually, in our question, we don't have minus 2s here. So since minus 2 is a constant, you can take it out and bring it to this side. So this implies as inverse Laplace transform of s over s squared plus 1 all in square is equal to. Already have minus here. So that minus and this minus get cancelled, and then we will have t by 2 into. That is the answer. That should be the answer. Yeah, I'm sorry. Here a is equal to 1, no? So there's a, no? So we have a here. I'm sorry. So this is actually we have got for SO s square plus 1. Okay. So similarly, you can do it for a. So if you have a something like here, say if you have similar one, Laplace inverse of s over s squared plus a squared all to the squared. Then if you find out, but here we know that Laplace inverse of a over s square plus a square is equal to sine 80. Sine 80. So if you say this is your fs, then f dash s is equal to what? Dash is equal to minus 2as square plus a a square all this. So this is your ft. This is nothing your ft. Okay, this is nothing your ft. Therefore, the inverse Laplace transform of minus 2as over s square plus a square whole square is equal to minus 1 to the power n. The value of n is equal to 1 because it's the first derivative. 1 into e to the power 1 into your ft, which is equal to sin ft. Okay, so here actually in the question we don't have minus 2a, therefore this is equal to, you can take minus 2a out because it is independent of the variable minus 2a, Laplace inverse transform of, you can say s over square plus a square whole square equal to minus e sin ht. Therefore, we can have inverse Laplace transform of s over s square plus a square all these square is equal to, that minus this we cancel with this minus, we have e over e into. We understand? We understand? Do you understand? Please respond.
Yes, sir.
Right. So next one, that is about next one, inverse Laplace transform of integrals. Okay, inverse Laplace transform of integral. Right? So that is very straightforward here. So next one, the sixth one, I think, the inverse Laplace transform of integral. Okay. So I am using the mouse to write it. Please apologize. So we know that Laplace transform of ft over t. Can anyone tell me what is the Laplace transform of ft over t? Laplace transform of ft over t is nothing but integration s to infinity f of u into t, isn't it? So that is the definition. So Laplace transform, when you divide the function by t, then its Laplace transform is equal to s to infinity f of u into t. Therefore, the inverse Laplace transform of the integration, this integration, s to infinity f of u into du equal to simply f of t divided by t. So if you want to find the inverse Laplace transform of integration, simply what you have to do is you have to divide the f of t by t. Okay? So this is very simple. So this is very straightforward. You can easily understand. This is directly coming from the definition of Laplace transform dividing by t. Okay, Laplace transform dividing ft by t. Okay, so if you have an example for this, so here we have the function 0 to infinity 1 over u minus 1 over u plus 1. Okay, so we want to find the inverse Laplace transform of s to infinity, because here we are changing the variable because we want to have the function in s. That is why we are changing it in u. So nothing difference. Okay. So here it is nothing wrong writing the function in u because ultimately we want the function in s. That is why we are putting as u. Okay. So this is we want to find 1 over u minus 1 over u plus 1. So we want to find the Laplace transform of integration of 1 over u minus 1 over u plus 1 from s to infinity. So this is what we want to find. So now it's actually integration is actually linear. That means that if you have a function like integration fx plus gx, okay, so this is equal to, you can write it as integration fx plus integration gx, isn't it? So always this is true because the integral operator is linear. Therefore, you can write this as this is equal to inverse Laplace transform of integration s to infinity 1 over u, and using the linearity property of inverse Laplace transform s to infinity 1 over u plus 1. You can write this. Now, so using this one, so when you have something like this, s to infinity f of u du, then that is ft over t. So can you tell me what is the inverse Laplace transform of 1 over u? What is the inverse Laplace transform of 1 over u? So this is actually du. So inverse Laplace transform of 1 over u is nothing but 1, no? Because if you Laplace transform of 1 is equal to what? Is equal to 1 over s, isn't it? Therefore, this is nothing but 1. Therefore, our ft is 1 and we have to divide it by t, isn't it? Our ft is 1, therefore we have to divide it by t. So that is 1 over t. Okay, minus, and what is the Laplace transform of okay, what is the inverse Laplace transform of 1 over s plus 1? What is the inverse Laplace transform of 1 over s plus 1? So this is nothing but the inverse Laplace transform of 1 over s minus 1, isn't it? So this is nothing but e to the power minus as. Sorry, e to the power as, but here a is equal to minus 1. Therefore, this is nothing but e to the power minus 2, isn't it? E to the power minus. So this is our ft. This is our ft. Therefore, for this one, since integration comes, we have to put it like e to the power minus t, and that one we have to divide it by t. So if we take t as a common factor, and write t into 1 minus. You understand this? You understand?
Yes, sir.
Right, fine. So you have to respond it, otherwise, I don't know whether you understand or not. Right. So now move to the next one, multiplication by s to the power n. Okay, multiplication by s to the power n. First, we'll talk about when multiplication by s, and then we'll talk about multiplication by s to the power n. So first one, the 7 one, we talk about multiplication by, so first one, okay, multiplication by s, okay, multiplication by s. Now, can anyone tell me what is the Laplace transform of f dash t? What is the Laplace transform of derivative? Can anyone tell me? First derivative. What is the Laplace transform of first derivative? Can anyone tell me? I'm waiting for your responses. Yeah, good. That is, we have S into Fs minus capital F0. You have to be careful. Minus capital F0. Therefore, if, look at this one, if capital F0 equal to 0, if capital, this part vanishes, if this part vanishes, then you can say that the inverse Laplace transform of S into Fs equal to okay. So this is true if F0 equals 0. Otherwise, you cannot write it. Okay. Otherwise, you cannot write this. Okay. Otherwise, you cannot write this. So you have to be careful with that. Okay. So this is the multiplication by S. Now, the second one, this is the first one. Okay, this is the multiplication by s to the power 1. Now, the second part, we'll talk about multiplication by s to the power n. So, we know that, so now the second part is multiplication by s to the power n. N belongs to set of natural. N belongs to set of natural. Then we know that Laplace, the transform of nth derivative. Laplace transform of nth derivative of a function equal to Sn into S minus what? Can anyone tell me what is minus what? Minus what? F0, no? Minus F0 minus, can anyone tell me? S n minus 1 into, sorry, I think this way, no? I think it should be like this. So s to the power n dfs, s to the power n minus 1 into x0 minus s to the power n minus 2 into f dash 0 and goes up to f minus 1. Is that correct? I have received one answer. Yes, good. So it goes up to f n minus 1 to the power 0. So now if these terms, f0, f dash 0, all are 0. If f0 equal f dash 0 equal dot, up to the last one, equals 0, then we can say that inverse Laplace transform of s to the power n into nth derivative of so simply, but this is true under this condition. This is true under this condition. If these are not 0, then you cannot try this one. So you have to be careful here. If these are not 0, then you cannot write this one. Under this condition only, we can write this one. Okay. So that is understood. Now let's have an example here. Yeah. This is multiplication by s, no? It's multiplication by s. So multiplication by s. So we are giving that Laplace transform of this one is this, then we want to find out. What's the question? Yeah, we want to find this one. Okay, so we want to find the Laplace transform of this one. So we'll do that example. So that example is we want to find the inverse Laplace transform of s squared over s squared plus 4 all this. Okay. So we want to find this answer. But if you can remember, I think under example, in example 7, we have got an answer for this. We have got from example 7. From example 7, you have the result that you have got an answer. We are using that. Actually, in the exam you have to do everything, but here, for the sake of finishing, we are doing it. So we have s over s squared plus a squared. Actually, we use derivative to find this answer. We got that t over 2a into sine 80. No, we got this answer. Therefore, if you put a equal 4, a equal 2. So if you put a equal 2, so if you put a equal 2, then you can write inverse Laplace transform of s over s squared plus 4 all in square is equal to t over 4 into sine 2. Isn't it sine 2? So now if you take this as your ft, now if you take this as your ft, then obviously we know that f of 0 equals f of 0 equals 0. Therefore, inverse Laplace transform of s squared. That means that s into this one. S into, if you say this is your fs, okay, s into fs. Actually, that is what we want. Actually, here you see, that is what we want. This is actually nothing but the inverse Laplace transform of s into fs. Okay. So if you take this as fs, we take this as our fs, then actually nothing, we want to find nothing but s into fs. Okay, so this is nothing but, because If 0 equals 0, then only we can use that. You have to remember this one, okay? You have to remember this one. Otherwise, we cannot use this one. Okay? So this is equal to what? This is equal to, according to this result, we have that the nth derivative. So because here s is equal to 1, we are multiplying by s to the power 1. Therefore, this is f dash f dash t. So this is equal to, if you differentiate this one, so that becomes t by 4 into, if you use the UV form, t by 4 into, if you differentiate sine t, that becomes 2 into cos 2t plus, and we get here, if you differentiate t, that is 1, we get 1 over 4 sine 2, we get 1 over 4 sine 2. Therefore, if you take 1 over 4 out, so that comes as 2t cos 2t plus sine 2. That is the answer. Yes. Okay. Now, so here you have to remember that if all these are 0 only, we can apply this result. Otherwise, we can't use this. Okay. These all have to be 0. So we have 2 more properties, so we can finish this handout today itself. So next one, the division by Sn. So division by Sn. Division by Sn. So we know that. So next one is division by Sn. This is the 8th one. Sorry, division by right. So actually, we know that Laplace transform of integration 0 to t fu. Can anyone tell me the answer for this one? The integration of differential Laplace transform of integration. Can anyone tell me the answer? Yes, good. That is equal to, we know that fs over s. Therefore, you can say that the inverse Laplace transform of fs by s, inverse Laplace transform of fs by fs equal to integration 0 to t fu t. So here we notice that, here we are saying that is n, but here we are having only one. Okay, so if you have many s, you have to apply this multi times. Okay, you have to apply this multiple times. Okay, So here we are having this for only one, when dividing by only one s. Okay, only one s. Now we'll have an example. So example. Okay. So okay, before we go to the handout example, let me take a simple example. Laplace transform of Laplace transform of, can anyone tell me Laplace transform of 1 over s into s minus s into s minus 1. So we can actually do this question in two ways. Actually, we can do this question in two ways. One is we can use partial fraction, because partial fraction is also. So I think you may have some questions in your tutorial. So partial fraction is also used in inverse Laplace transform. Okay? We all are familiar with this partial fraction. What is called the partial fraction? Okay, this example is not in your handout. Huh? So this is partial fraction. That is method one. We can actually do some partial fraction of this one. So if you do partial fraction of this s into s minus 1, you can write this as, I think you can write it like 1 over s minus 1 over s minus 1 minus 1 over s. No? So to multiply s here, yeah, this is the correct partial fraction of this one. So then this is equal. So method one. Huh? So this is equal to the inverse Laplace transform of 1 over s minus 1 minus 1. So this is equal to, using the linearity property, you can write this as 1 over s minus 1 minus Laplace transform of. So can anyone tell me the answer? What is the inverse Laplace transform of 1 over s minus 1? Can anyone tell me the answer? What is the inverse Laplace transform of 1 over s minus 1? I'm waiting for your result. What is the inverse Laplace transform of 1 over s minus 1? What is the inverse Laplace transform of 1 over s minus 1? Yes. E to the power minus t or e to the power t? Yes, that is e to the power t, because s minus a, no? So this is e to the power t minus. What is the Laplace transform of 1 inverse Laplace transform of 1 over s? What is the inverse Laplace transform of 1 over s? Yes, good. That is 1. So that is 1. So that is the answer. So this is method 1. So now we'll use method 2. So we know that inverse Laplace transform of 1 over s minus 1, which is equal to, we know that e to the power t. Therefore, inverse Laplace transform of 1 over s minus 1 divided by s is equal to the inverse Laplace transform of 1 over s into s minus 1. So according to this one, it is actually 0 to t fu du. So this is our fu. This is our ft now. This is our ft now. Therefore, this is equal to, in fact, 0 to t we have to change the variable because finally we want to get the answer in t. Therefore, my fu. So my fu is actually e to the power u into, isn't it? E to the power u. So this is equal to, if you integrate e to the power u, that is same as e to the power u, and you have to put the answer 0 to t. So this is equal to e to the power t minus e to the power 0, which you get it as e to the power t minus. So we are getting the same answer. So we are getting the same answer. Okay. So this way also we are getting the same answer. This way also we are getting the same answer. Do you understand this? Do you understand this?
Yes, sir.
Okay, fine. Right. So now we'll go to the handout example. In this handout example, we have 1 over s cube square plus 1. Okay, so we want to find the inverse Laplace transform of 1 over s cube square plus 1. So here, if you see here, actually this theorem works for s n equal 1 only, because we can use s equal 1 only, isn't it? Therefore, if you have s to the power n, then we have to use this repeated. Okay, we have to use this repeated. Therefore, so first we will find the inverse Laplace transform of 1 over s into s square plus 1. So inverse Laplace transform s square, this one. First we'll find this one. So to find this one, we find the inverse Laplace transform of 1 over s square plus 1. Then what is the Laplace transform of 1 over s square plus 1? Can anyone tell me the answer of this one? This is equal to sine t, no? This is equal to sine. Therefore, actually, if you divide by s, you will get this one. Therefore, the inverse Laplace transform of 1 over s into s square plus 1 equal to the integration 0 to t. You have to change the variable. This is ft. Okay, this is ft. So that is equal to 0 to t equal to sine u. So if you integrate sine u, you get minus cos u. And you have to substitute 0 to t. So if you substitute 0 to t, then you will get 1 minus cos t. So now, again we have to divide this by s to get this integrations. Now the second one, we'll find the Laplace inverse of 1 over s square plus 1. This is nothing but this is nothing but 0 to t of this one. Now this is the ft. Now this is our new ft. This is our new ft. So you have to change everything by u. So that is 1 minus cos u. So if you integrate this one, you get u minus sine u. Then you have to substitute 0 to t. So if you substitute 0 to t, you will get t minus sine. Because when you substitute t, u equals 0, that becomes 0. So this is now your new ft. is now union. Then to find L inverse 1 over S cube, 1 more S, we are dividing by 1 more S. So S square plus 1 equal to, again we have to integrate 0 to t. Now your function is 2 minus sine u. So you see, we don't have a formula for s to the power n. So we have to do one after the other. So you have to be careful here. So if you integrate this one, we get here u squared by 2 minus cos u, but already we have minus here, therefore plus cos u. Plus cos u, you have to substitute 0 to t. So if you substitute t here, that becomes e squared by 2 plus cos t. And if you substitute 0, this becomes 0 plus 1. So which is equal to e squared by 2 plus cos t. Yeah, we're getting the same answer. Okay, so t squared by 2 plus cos t minus 1. You understand? Do you understand this?
Yes, sir.
Okay. Then we are moving to the last one, the 9th one. This is convolution here. So this is very important one, convolution. Convolution theorem. Let's first talk about convolution theorem. What is convolution theorem? Now, actually, this is not only in Laplace transform. This is one of the, convolution theorem is one of the broadest one in mathematics. Okay, this is not relevant to Laplace transform only. Okay, in many places we are using this convolution theorem. Okay, so now say we have two functions. Let ft comma gt be piecewise continuous and exponential order functions. So we are saying because we are ensuring that ft and gt have Laplace transform, because these are the condition required for the existence of sufficient condition required for existence of Laplace transform. So we are defining, or we are saying that ft and gt be piecewise continuous function and exponential order. Then the convolution between f and g, convolution, the convolution, okay, then the convolution between ft and gt is defined this way: ft star, this is the notation for convolution. This is actually, if you write like this, it is convolution. ft into gt, it is not multiplication, it is actually denoting the convolution. ft into gt is defined as the convolution between f and g is given by this integration 0 to t, 0 to t f of u into g of t minus u into d. Okay, so this is how the convolution is given. Convolution is given. conversion is given this way. Right? Say for an example, if f of t is equal to, say example, f of t is equal to sine t, then gt equal to, say, e to the power t, then the conversion between f and gt is defined as is given by this integration. Actually, conversion is an operation. Okay, so 0 to t sine t, you can take any function because convolution is commutative. Later you can see that. Sine t e to the power t minus, sorry, sine u, I'm sorry, sine u e to the power t minus u into. So this is how it is defined. Okay, right. So that is the definition of convolution. Then convolution actually satisfy these conditions. If you have three functions f star g plus t, so associative law holds for convolution. Commutative law also holds for convolution. What is the meaning of commutative? So convolution commutative mean what? That means ft star gt equal to gt star ft. Okay, so that means that integration 0 to t, okay, 0 to t f of u into g of u minus t into du is equal to integration 0 to t g into f of, sorry, this is a t minus, yeah, sorry. So f of, okay, so this is for the associative. Similarly you can say that it is associative law also holds, distributive law also holds. Okay, so these are the properties, but if you know this property, it is enough. You don't need to prove this one because our topic is actually Laplace transform. But this convolution, as I told you, this is the broadest, this is somewhat broader concept in mathematics. Okay, so here we are using this convolution theorem in Laplace transform. That's all. Okay, now we'll come to the convolution of Laplace transform. Okay, so it says that, look at here. If Laplace transform of Fs is equal to this one and Gs is equal to this one. So you see, when two functions are multiplied, okay, when two functions are multiplied, say for an example here, now look at here, we have the inverse Laplace transform of Fs is equal to Ft. The inverse Laplace transform of Fs is equal to Ft, and the inverse Laplace transform of Gs is equal to, there are two functions, okay? Gs is equal to Gt. Then we want to find the inverse Laplace transform of the multiplication of these Fs into Gs. Okay, this is not convolution, this is the ordinary multiplication, okay? This is ordinary multiplication, don't misunderstand, okay? This is nothing, this is just our usual multiplication. Then this is equal to integration of 0 to t f of u into t of t minus u into t. So this is what actually. This part is what actually. This is nothing. This is nothing actually. This is convolution of ft into. Okay. This is nothing but convolution of ft. Therefore, if two functions are multiplied, then it is same as, so then its inverse Laplace transform is actually equal to the convolution of ft to g. Okay, so that is what this says here. Look at here. The inverse Laplace transform, this one is this. Therefore, conversely, you can write conversely. Okay, so actually we didn't study this. We didn't study this in our when we study Laplace transform, because here only we see that it's a very important one. Okay, but conversely, what you can write? So if you have the, if you know the inverse of this one, then from this one you can write this one. From this one you can write Laplace transform of 0 to t f of u into g of t minus u into du. Okay, then this is equal to fs into gs. Okay, fs into gs. So you see that. So when you have an integration in this form, when you have an integration in this form, then you can use this one. Okay, but mainly we use this convolution for the Laplace inverse transform. Inverse Laplace transform. Okay, so I hope you understand. Do you understand this one? Do you understand, students?
Yes, sir.
Okay, fine. Then if you understand, that is fine. Okay, so actually, yeah, that is fs into gs. Now we'll have an example and we'll find out the class. So that is, we want to find out the inverse Laplace transform, this one. So we are going to use the convolution theorem to find the Laplace transform, this one. So we have to find s plus 3 into s minus 1. So homework, okay, use partial fraction method. So use partial fraction to find the answer of this one. Partial fraction, and then you do the partial fraction and use the ordinary method to find the partial fraction. No, partial fraction. Please try this as the next class. I will ask this. Okay. Next class I will ask one of you to do this using the partial fraction. So use partial fraction and get the answer. Now this is method 1. Okay. This is method 1. Now we'll do method 2. That is using the convolution. So if you take this as your, okay, now I have the inverse Laplace transform of 1 over s plus 3 into 1 over s minus 1. 1 over s minus 3, 1 over s plus 1. So if I take this as my, if I take this as my fs, you can take this also fs, no problem, huh? Because we know that convolution is commutative now, therefore no problem. And if you take this as your gs, then we know that the inverse Laplace transform of 1 over equal to e to the power minus 3, isn't it? And similarly, the inverse Laplace transform of 1 over s minus 1 equal to e to the power t. So if you say this is your ft, because you have taken this as your fs, no? So if you say this is your ft, and then this is your gt, then using the convolution, theorem, you can say that this is equal to the integration 0 to t, okay, fu means e to the power minus 3u into gt minus u. So if gt is equal to t, no, so e to the power, wherever you have, so from this one, okay, you can write g t minus u mean wherever you have t, you have to replace it by t minus u. So g t minus u is e to the power t minus u. So you can put it like e to the power t minus u into t. So if you simplify this one, this is e to the power minus 3u, e to the power t minus 3u. Then if you use the thing and simplify, then that is equal to 0 to t. Okay, you can write it as e to the power t minus 3. Sorry, I think sorry, wait a minute. Yeah, we have minus 3u here and minus 3u, and here you have minus u. Therefore, e to the power minus 4u. No? So if you use the laws of indices, that becomes. So I will finish it within 2 minutes. Okay, don't worry. E to the power minus t into t. So here the variable, integration variable is u. Therefore, you can take out t out, no problem. So this is equal to actually e to the power t into integration 0 to t e to the power minus 4u. So this is equal to e to the power t, and if you integrate this, you get minus 1 over 4 e to the power minus 4. So that is equal to, here you have to substitute 0 to t. So e to the power t, and if you take minus 1 over 4 out, so that becomes minus 1 over 4. Minus 1 over 4. If you substitute t, it becomes e to the power minus 40 minus e to the power 0, which is 1. Therefore, if you multiply by the whole, if you multiply by minus 1, then you can write this as 1 minus e to the power minus 3. Okay, what I am doing here, this is equal to 1, and I am multiplying by minus 1, and I am getting this answer. Okay, that should be the answer, I think. You see, we are getting this. Sorry, I have to multiply this by t also, no? Yeah, so this becomes e to the power t. I'm sorry. Because when you multiply, this is 1, no? So when you multiply by 1, then you must get. So that is the answer. Do you understand this? Do you understand?
Yes, sir.
Yes, sir.
Right. Okay. Fine. Then please try this. Please try this as using the partial fraction method. Okay. So if you try to do the partial fraction, so we have 1 over s plus 3 into s minus 1. You can definitely do a partial fraction. You can write it as a over s plus 3 plus b over s minus 1. You can solve this equation and find a and b, and then you can easily use the method and you can get this answer. Okay, right. So shall we wind up now? Okay, so that is the end of this inverse Laplace transform. The next class I will start application of Laplace transform, and hopefully I think I can finish it in the next class, and week after next I can do this, because I am thinking of real analysis, because we want to have some extra classes. If we have one extra class for real analysis and one extra class for integral transform, we can somehow complete the syllabus before the examination. Okay, because we have to study Fourier transform and the integral transform, and we have to study functions under real analysis. So we need some more time, because I am teaching somewhat slowly. Therefore, we need some more time. Anyway, so I stop for today, and thank you very much for your cooperation. So please, I have already shared you the tutorial on inverse Laplace transform. Please work on that, and if you have any doubts, please ask me. Okay, already I have shared you the tutorial of that. Okay, so that's the end of this. Okay, thank you very much. Anyway, I will send this writing pad to you. Okay, so I will save this and send it to you. Okay, if you have any doubt, you can use that. Okay, shall we wind up then?